Okay, what I wanted to go over with everyone today, both here on campus, off campus, or if you watch this later, is finding area not only under a curve, but also between two curves. So I want to start with the area under a curve first and what that really means. Oh, okay. Area under a curve is actually a region bounded by your given function and also the x-axis here between some closed interval from A to B. So this is what the general graph looks like, general picture looks like, finding the with an area under a curve bounded by the x-axis. Now, we have discussed finding area under a curve by using what's called Riemann sums, where you would draw rectangles, individual rectangles under the region under the curve, and then find the area of each individual rectangle and then add those together. The drawback to that method is that your area is not going to be as exact as what we're about to discuss now. To find the area under a curve bounded by the x-axis, you simply use this formula here. And that is integral going from A to B, those are your endpoints, of your given function dx. So that is the general formula of finding the area under a curve, excuse me, bounded by the x-axis. So let me screenshot this first example and go over it with y'all. And let me switch screens here. Here on campus, can you see that okay? Okay. Find the area in the first quadrant bounded by f of x equal to 4x minus x squared and the x-axis. Now, if a graph is not given for you, then graph your function on Desmos. Now, with graphing, you can find your endpoints or your interval. So our interval goes from 0 to 4. So let's set up our formula. We're going from 0 to 4 of f of x, which is 4x minus x squared dx. And all we do is just integrate each part. So the integral of 4x, remember we are undoing the power rule, we're actually taking the antiderivative. And instead of subtracting 1 from the original exponent, you're actually adding 1 to it. And instead of multiplying 1 by 4, you divide your antiderivative by your new exponent. So this will become 4x squared over 2, or just 2x squared for that first integral. And you do the same thing with x squared. You're taking the antiderivative by adding 1 to the original exponent and then dividing your antiderivative by the new exponent. So that will give us x cubed over 3. And we're evaluating this from 0 to 4. Now, the fundamental theorem of calculus, part 2, states that you plug in your upper limit of integration first. So we'll plug in 4 everywhere we see an x first. So that would be 2 times 4 squared. Two times 4 squared minus 4 cubed over 3. And there is a minus sign in between your substitutions. And the second go around, everywhere you see an x, you'll plug in the lower limit of integration, 0. So we have 2 times 0 squared minus 0 cubed over 3. And actually, that entire second part goes to 0. So for the first substitution, 4 squared is 16. Times 2 is 32. Right here, 4 cubed is 64 over 3. Now let's rewrite 32 as something over 3. That way we can easily subtract the fractions. So 32 can be rewritten as 96 over 3 minus 64 over 3. So our area under the curve is exactly 32 over 3 square units. Again, with this particular method, you get versus the Riemann sum, you get a more accurate or exact answer. Any questions about this first problem? And I'll leave it up here in case anybody wants to snap a picture of it with your phone. I will share this recording later. I apologize, I forgot to share the last recording with you guys, but it covered mainly area under the curve. All right, let's look at another problem. Let me just screenshot it for us. All right, this example, calculate the area bounded by y equal to x to the negative 1 power and the x-axis between x is equal to 1 and x is equal to 4. Y equal to x to the negative 1 power is the same thing as 1 over x. And again, if the graph is not provided for you, plug it into Desmos. So this is the area that we are trying to find. So let's use our area formula to set up our integral. We have area equal to the integral, which is going from 1 to 4, of 1 over x dx. Now, the integral of 1 over x dx, that's a special formula. That is actually the natural log of x. Again, the integral of 1 over x dx is equal to natural log of x. Now we're ready to use the fundamental theorem of calculus, part 2, to find our actual area. So we plug in the upper limit of integration first, and that gives us natural log of 4. In the fundamental theorem of calculus part 2, there's a mandatory minus sign in between your substitutions. And the second go around, we'll replace x with 1. That will be natural log of 1. Well, the natural log of 1 is 0. So our final area is exactly natural log of 4 square units. Now, if MyMathLab wants your answer as a decimal, then you would just take the natural log of 4 and get roughly 1.386. That is only if MyMathLab wants a decimal answer. Are there any questions about this problem? What about here on campus? Any questions? Oh, and by the way, I'm still recording, but just want to tell you here on campus, I got your email and I did take care of that for you. You're welcome. All right, let's look at the next problem. Next problem is a trig function. Find the area bounded by the curve y equal to sine x and the x-axis between x equal to 0 and x equal to pi. The required area is shown in the figure. Note that it lies entirely above the x-axis. Because we know how the sine curve behaves, part of it goes below the x-axis. So that's why this phrase has to be stated, or else you'll have several curves that you got to find the area for. All right, well, let's use our area formula and set up our integral. Our region under the curve is going from 0 to pi. The integral of sine x dx. The integral of sine x, and by the way, you can search on Google and find a printable version that lists all the basic trig integrals. The integral of sine x is negative cosine x. And we are evaluating that from 0 to pi. First up, using the fundamental theorem of calculus part 2, we'll plug in pi for x minus, and there's a negative in front of the cosine, so bring that down. Remember that minus sign in the middle is a required part of your fundamental theorem of calculus. And the second time around, in place of x, you'll plug in 0, the lower limit of integration. Now, cosine of pi on your unit circle is negative 1. And cosine 0 is 1, but it's negative. Now, when we take care of the double negatives, they turn into positive signs. So we're left with 1 plus 1. So the area under our curve going from 0 to pi is exactly 2 square units. Are there any questions about finding the area under a curve that is bounded by the x-axis? Well, what if you have two curves and you need to find the area between them? So let me give you a little background information and also a specific formula that we'll be using. Hang on just a second. Go. Now let's say you got two curves pictured here with the area A, and you got to find the area between these two curves going from closed interval A to B. If your oops, sorry. If your functions are given in terms of x, then you will use this specific formula to find the area between two curves. It's still going from the closed interval from A to B, and I usually do top curve minus bottom curve, or you can say upper curve minus the lower curve. In other words, the upper curve is the curve that's on top, and the lower curve is the one that's on the bottom. So only use this particular area formula if your functions are given in terms of x. Now, if your functions are given in terms of y, then you would use this specific formula right here. And let me actually enlarge that for everybody. Again, if your functions are given in terms of y, then you need to use this specific formula right here. You would still have the interval, closed interval, going from what lower limit to upper limit of integration, but you will, instead of saying top curve minus bottom curve, you will say right curve minus left curve. That's how you would set it up if your functions are given in terms of y. We'll deal with that in just a moment. But let's look at this first example. And I'm going to screenshot the problem itself as well as the figure. All right, let's see what we're trying to find. Find the area bounded by the graphs of y equal to 3 minus x and y equal to x squared minus 9. And we don't need to worry about solving or setting these equal to each other to find the boundaries or the closed intervals, because the graph easily shows them for us. So let's set up our formula. We are going from -4 to +3. And because we're given two curves, we got to find the area between the two curves. And because our functions are given in terms of x, we're going to use the formula top curve minus bottom curve. All right, so according to our graph, the 3 minus x is our top curve, and the x squared minus 9 is our bottom curve. Now, before we integrate, we need to distribute that negative sign in the middle to everything in the bottom curve. So we have 3 minus x squared plus 9. And that simplifies to negative x squared minus x plus 12 dx. Now we're ready to integrate or take the antiderivative of each term. So the negative x squared will become negative x cubed over 3. The antiderivative of negative x is negative x squared over 2. And the antiderivative of 12 is just plus 12x. Now we're ready to plug in our limits of integration, starting with the top one, the 3 here. So everywhere we see an x, we'll plug in 3. So we have negative 3 cubed over 3 minus 3 squared over 2 plus 12 times 3. We need a mandatory minus sign in between our substitutions. And the second go around, we'll plug in -4, our lower limit of integration. And just be careful with your negative signs. We have a negative and then -4 cubed all over 3 minus a -4 quantity squared over 2 plus 12 times -4. Let's simplify the top part that's in light blue. -3 cubed is -27. Divided by 3 will give us -9. Here, 3 squared is 9, and that's over 2. And then 12 times 3 is a positive 36. Minus, right here, -4 cubed in green is -63. I'm sorry, -64. Times the negative that's already out there gives us a positive 64 over 3. Here in the middle, -4 squared is 16. And -16 divided by 2 is -8. And then the last part before we put everything together, 12 times -4 is -48. Now let me stop for a second. Were there any questions off campus or here on campus? Let me erase part of the right-hand side so we can continue. All right, in blue, when we combine everything together, we get, I believe that's 27 minus 9 halves minus, and in green, when we combine our terms, we get 64 over 3 minus 56. Now let's go ahead and distribute that minus sign in the middle and bring down everything else. So that would be minus 64 over 3 plus 56. 27 plus 56 is 83. Now, to combine everything together easier way, we need to rewrite each part as something over 6 because 6 is the common denominator. So 83 we can write as 258 over 6. Oh no, that is not right. Hold on. Hold on just a second. Let's see, 83 times 6. Yeah, sorry about that. That should be rewritten as 498 over 6. The 9 over 2 can be rewritten as 27 over 6. And 64 over 3 can be rewritten as negative 128 over 6. Now all we do is subtract the numerators. And our final area is 343 all over 6. Again, are there any questions before we look at the next problem? All right, let's look at another example in which we're given two curves and we got to find the area between them. So let me copy and paste this next example. Find the area between the curves y equal to x squared and y equal to x cubed. And we can tell, according to the graph, that our boundaries go from 0 to 1. Now, because our functions are in terms of x, we're going to use the formula top curve minus the bottom curve. And according to our graph, this is the reason why graphing is so important. That way you know which curve is top, bottom, right, or left. Our top curve is x squared, And our bottom curve is x cubed. And we can immediately take the antiderivative of each curve. The integral of x squared is x cubed over 3. And the antiderivative of x cubed is x to the 4th over 4. And we are finding the area going from 0 to 1. Now, according to the fundamental theorem of calculus, part 2, you plug in your upper limit of integration, in this case 1, you plug that in first. So we have 1 cubed over 3 minus 1 to the 4th over 4. Don't forget there's a minus sign in between your substitutions. And the second go around, we'll plug in 0, our lower limit of integration. Well, the second time around when we plugged in 0, everything goes to 0. So we don't have to worry about that part. First part, we have just 1/3 minus 1/4. Our least common denominator among the fractions is 12. So we can rewrite 1/3 as 4/12. And we can rewrite 1/4 as 3/12. So the area under the curve depicted in yellow in our graph is 1/12 square units. And that makes sense because our curves are so close together. So that means the area is not going to be that big. Are there any questions about this area problem? All right, so far we've looked at curves that have been in terms of x. But what if you have a problem where your functions are in terms of y? So let me walk you through how to find this particular area. Oh, let me copy and paste the graph too. And also let me copy and paste the specific formula we need to use. Okay, anytime that you have to find the area between two curves and each function is in terms of y, then you cannot use top minus bottom formula. You have to use this formula here to find the area. You just take the right curve minus the left curve. Now it's kind of hard to see, I'm sorry, but let's see. Right here, this curve in green is actually x equal to 1 minus y squared. So that is actually the right curve. Oh, and according to our graph, Anytime your curves or functions are in terms of y, then you look to the y-axis for your limits of integration. So we don't use the x's, we instead see where y starts and where y ends. So our region goes from -1 to 1. The right curve, which is 1 minus y squared, minus the left curve, y squared minus 1, dy. Now, before we integrate, we must distribute that negative sign in the middle to everything that's in the second function. So when we do that, we get 1 minus y squared minus y squared plus 1. Well, the y squareds cancel. No, actually, they don't. I'm sorry. They don't cancel out. What we're left with when we combine the y squareds is -2y squared plus 2. Now I'm going to erase the graph because we don't need it anymore. And let's integrate. The integral of -2y squared is -2y cubed over 3. And the integral of a positive 2 is just a positive 2y. And we're evaluating this from -1 to +1. Now, according to your fundamental theorem of calculus part 2, you plug in your upper limit of integration first. So we'll do that carefully. Minus, remember that minus sign is required. And the second time around, we'll plug in our lower limit of integration, -1. So we got -2 times -1 cubed over 3 plus 2 times -1. Right here, back in blue, 1 cubed is 1 times -2 gives us -2/3 plus 2 minus, right here, -1 cubed is -1 times 2 times -2, I'm sorry, gives us a positive 2, or 2/3, minus 2. Now let's distribute that negative sign in the middle to everything in the second part. And let me erase some of this again so we'll have more room to work. So we have -2/3 plus 2 minus 2/3 plus 2. Now, when we combine our fractions and our integers, that will give us -4/3. Oh, you're fine. That will give us negative 4/3 plus 4. Now, to combine our fraction with our integer, make the 4 as 12/3. So our final area under the curve is 8/3 square units. By the way, if you get a negative area, you need to check your setup because for most of the problems, you should get a positive area. Are there any questions about finding the area under a curve or between curves?